with these examples. So we started chapter 4. Somehow I've got to get you guys to get caught up with me though. You want to ask anything before I get started? Yes, sir.
Is there a trick to remember all the values on the unit circle?
Well, I showed you that table last time. If you build that table, you've got,
Yeah, this one?
no, even before we covered the unit
Oh,
circle,
Yeah.
right? If you can remember it in table form, then you can put it on the circle pretty quickly.
Yes.
So what I'm talking about is when we had angles. All right, surely I have paper. So the question was, how to remember those values? If you remember the first quadrant, you're rocking and rolling. And so when we talked about angles, we used a theta here. When we talked about arc length, we used an S. We did this in degrees, and then recently we did it in radians, so I'll do it in both. We had 0 degrees or 0 radians. 30 degrees, which is pi over 6 radians. 45 degrees was pi over 4 radians. 60 degrees is pi over 3 radians. And 90 degrees was pi over 2 radians. And then to remember the values, remember that the sine is always the y value. I do this backwards to make the tangent function real easy. And then the cosine of that value. Then if you want to add a column for tangent, you do the y over the x. So you just count, right? 0, 1, 2, 3, 4. And then go upwards, 0, 1, 2, 3, 4. Then we take the square roots of each of those numbers. Divide by 2. Then the last step is to simplify. Square root of 0 is 0. 0 divided by any number is 0. Square root of 1 is 1, so this one simplifies to 1/2. The next two stay put. Square root of 2 over 2, square root of 3 over 2. Square root of 4 is 2. 2 divided by 2 is 1. And so the same deal here. Then the tangent is the y divided by x, so 0 divided by 1 is 0. 1/2 divided by square root of 3 over 2 is 1 over the square root of 3, or square root of 3 over 3. The square root of 2 over 2 divided by the square root of 2 over 2 is just 1. Square root of 3 over 2 divided by 1/2 is the square root of 3, and 1 divided by 0 is undefined. If you can remember those in the first quadrant, then you can get the other ordered pairs in the other quadrants using the symmetry of the circle and just being able to count. Yes.
So that one's just the same as the one we did before?
Exactly. If we put them on the circle in the first quadrant, they would look like this. Here we would have our unit circle. So here's our 0 degrees, 0 radians, and the ordered pair there is 1, 0. Here's our 90 degrees, pi over 2 radians, and our ordered pair there is 0, 1. And 45 degrees was in the middle. 45 degrees was pi over 4 radians, and the ordered pair there was the square root of 2 over 2, square root of 2 over 2. Then if I divide this circle here, if I ignore that arc and divide it into 3 equal pieces, maybe here and here, those would be the pi 6s. That's 1 pi 6, then here's 2 pi 6, but 2 pi 6 simplifies to pi thirds. So this first dotted line here is pi over 6. Pi over 6 was the 30-degree line. And the ordered pair right here was at pi over 6, x is square root of 3 over 2, 3 I said, and y is a half at pi over 3, which was 60 degrees, x is a half, and y is square root of 3 over 2. So it's the same numbers that are in this table. And then you just use the symmetry that the top half of the circle is pi. So if you cut that into 6/6, you'll get the 5 pi sixths and the 2 pi thirds. Cut it in half and you'll get the 3 pi over 4 and so forth. Okay?
You have a nifty way of remembering the exercise is doing, but you take square root of 3 over 2. Sometimes I get
Have you tried electric shock therapy? When you get them flipped, go. Looking at the picture helps because square root of 3 over 2 is a bigger number than a half. And so if I'm wondering, let's see, what is the y value here? Is it going to be a half or square root of 3 over 2? Well, if you look at the picture, the y value is much bigger than the x value. So that tells me the x is going to be the smaller number. Does that help in any way? No? Right, because square root of 3 is almost the square root of 4, right? So it's close to 2. Square root of 3 over 2 is about 0.88, 0.87, somewhere in that neighborhood. It is just a memory thing. I mean, you guys can remember all those stupid little tricks in video games. I don't know how you remember that.
It's not true.
This is 5 things to remember. It always amazed me when my kids would do those games and I think, how do you know to go in that room? Oh, how do you know which button to push? That's what always bothered me. I was clicking away and don't even know where my thumbs and fingers are going. What else you need? Practice, absolutely. So blow off those other classes. Spend about a week or 2 on Trig only, and you'll see the results. The school invites you not to come back for a while. I know you guys are busy with your majors and other things like that, but you gotta learn to juggle. That's the real world. We've all got to do more things than we think that we can do. That's why there's 24 hours in a day. You can sleep after you graduate. Or so I say. Last night I'm on the computer late for me answering trig questions. So all night long I'm dreaming of trig. Barely slept. I'm serious. I can't get on the computer at night because I just too much for my poor brain. I got to sit on the couch with a glass of wine and
I'm sorry you drink.
I know. I was showing folks the unit circle all night long. And what's the first thing I do this morning? Blah. And I like trig, but not when I'm sleeping. Why can't I dream of puppies and butterflies? I don't know. Okay, so we were talking about linear and angular velocity. A velocity in any way, shape, or form is a rate of change. So it's a with respect to time. Angular velocity measures how much or how the angle is changing at what rate. So it's the total movement of the angle, theta, divided by time. Linear velocity, well, it's really not linear because we got a point moving on a circle. Maybe you want to call it circular velocity, but it's how fast the point moves along the arc. So it's the length of the arc divided by the time. And so we had these formulas up here that the angular velocity is the ratio of the angle, theta, that's being traversed to the amount of time it takes to traverse that angle. So typically our angular velocity is measured in radians per time unit, seconds, minutes, hours, but radians per time unit. Theta is always in radians. Finding angular velocity is pretty much just a matter of converting units. You're told how long it takes something to make a rotation. A rotation in trig is 2 pi radians, so you convert that rotation into radians per time unit. So the easy example was that it takes the Earth 24 hours to rotate on its axis. So 24 hours is the time period to make one revolution. So I start out with, I want to find the angular speed. So it's one revolution is done in 24 hours, but one revolution is equivalent to 2 pi radians. And so if I want radians per hour, I just multiply by this conversion factor, and that gives me 2 pi radians per 24 hours. Now simplify that, and it gives you pi over 12 radians per hour. Oh, I want the one without the work on it. Here it is underneath. So it's a matter of converting units. Put your described a revolution, how long it takes. We know there's 2 pi radians in a complete revolution around the circle. Cancels revolutions and leaves you radians per time unit. So in my next example, let's see what you can see. Got a little bit bigger. So there's the calculation on the radians per hour. Let's look at the ceiling fan here. A ceiling fan rotates 30 times per minute. Find its angular velocity in radians per minute and in radians per hour. So let's first get the angular velocity in radians per minute. So we start with the fact that it takes 30 revolutions per 1 minute. 30 revolutions per 1 minute. Then a revolution, one revolution, is 2 pi radians. So that'll cancel the revolutions and leave me radians per minute. So that says that it takes, that its angular velocity is 60 pi radians per 1 minute. That's the radians per minute calculation. To get into radians per hour, we just start from that and convert minutes to hours. So if I start with 60 pi radians per minute and I need minutes to cancel, then I put minutes on top here, that there are 60 of those in 1 hour. So that cancels my minutes and leaves us with radians per hour. 60 times 60 is 3,600. Don't forget the pi, and that's going to be radians per hour. So finding angular velocity is a matter of converting units. Now, if we're interested in linear velocity, or how the point, what the rate of speed is of the point moving around the circle, then we take the distance traversed, which was the arc length, and divide it by time. So distance traversed divided by time. But then in the last section, we had that formula for S. S is R times theta. So I put the R times theta where the S is. But in this fraction, there's a theta over T. Well, up here, theta over T was omega. That was the angular velocity. So you can also write velocity in terms of the radius times the angular velocity. Any version of that works, just depending on what you think of doing, what it is that you're given. So I want to look at using the Earth as our example from the first thing. Find the linear velocity of a point on the Earth's surface in one rotation. Well, we computed the angular velocity, so I may as well use this form of the velocity formula, the linear velocity formula. It's the radius times the angular velocity. I give you the radius of the Earth in miles, 4,000 miles, about 6,400 kilometers. And we want to put our answer in miles per hour. So from the earlier example, we had that omega was pi over 12 radians per hour. And we have the radius is 4,000 miles. And so I'm just going to use velocity is r times omega. And so if I multiply r with omega, the 4,000 times pi over 12 is going to be the linear velocity. And I computed that to miles per hour. That's roughly equal to 1,047 miles per hour. That sounds pretty dang fast, but we've got a very large radius on this Earth. So that means a point on the Earth is feeling movement of 1,047 miles per hour. And you don't fall off the Earth moving at that velocity because we have gravity. Let's do the same for the ceiling fan. Find how fast a point on the tip of the ceiling fan is rotating if the ceiling fan has a blade that's 2 feet long. So find the linear velocity of the fan blade in miles per hour. So up at the earlier example, we found the angular velocity of the ceiling fan in radians per hour. So I'm going to use this 3,600 pi. So earlier, we found that omega was 3,600 pi radians per hour. And now we're going to use the fact that velocity is the radius times omega. Well, my radius is given in 2 feet. So I have 2 feet that I need to convert to miles if I want to get things in miles per hour. So I tell you down here that it takes 5,280 feet to make a mile. So to convert this to miles, I say that there are 5,280 feet in 1 mile. So that now gives my fan blade as a mile measurement. 2 divided by 5,280 miles is the radius of the fan. So don't really call that R, not RW. I'm just converting R first. So there's the radius. Now velocity is going to be R times omega. So I take my radius, 2 divided by 5,280. And I'm going to multiply it with my radius, which is 3,600 pi. This is miles, this is radians. When you multiply miles and radians, we'll get the linear measurement of miles, because that'll be a radians per mile. And then we multiply by per hour. And so this is going to give me 7,200, 2 times 3,600 pi over 5,280. And that will now be in miles per hour. And as a decimal, that one is about 4.28, maybe about 4.3 miles per hour. That make sense? All right, I got to flip the page over. Get you all copied up here. Am I writing big enough for you guys in the back to see? Okay, I'm gonna flip the page. We're gonna do the same thing with a Ferris wheel. A Ferris wheel rotates, come on, Blur, 3 times each minute. Passengers sit in seats that are 25 feet from the center of the radius, from the center of the wheel. So that 25 feet will give us the radius of a person riding this Ferris wheel. Find the angular velocity of the wheel in radians per minute. Then find the linear velocity of the passengers in feet per minute. So again, the angular velocity just means convert from your revolution rate by multiplying by 2 pi radians per revolution. So we're told in the first sentence that it rotates 3 times per minute. So 3 rotations per 1 minute. We're working on omega. And a rotation is 2 pi radians. So I'm going to cancel rotations. 1 rotation is 2 pi radians. And when I cancel there, I get radians per minute. So 3 times 2 pi gives me 6 pi radians per minute as the angular velocity. Now to find the linear velocity of the passenger sitting in one of these little Ferris wheel cars, you take the angular velocity times the radius. Linear velocity is equal to the radius times the angular velocity. So my radius is 25 feet. And my angular velocity is 6 pi radians per minute. Let's see, 6 times 25 is about 150. 150 pi, and then we'll worry about, now we're on the circumference. So these will be in feet per minute. That's about 471 feet per minute. So it takes about 1 minute for a person on this roller, the Ferris wheel, to go 471 feet around the arc. So if the diameter, if the radius is 25 feet, how long does it take them to do this ride here? The circumference is 2 pi r. R was 25. So 50 pi is the radius. Pi is about 3-ish, so 150 feet-ish. You get all the way around, they're doing 471 feet per minute. Let's do the same thing with a satellite here. Satellite traveling in a circular orbit, 1,800 kilometers above the surface of the Earth, takes 2.5 hours to make the orbit. If the radius of the Earth is 6,400 kilometers, approximate the linear speed of the satellite in kilometers per hour, and then find the distance the satellite travels in 4 hours. So maybe what you've seen is computing linear velocity is easy if you have angular velocity. So let me see if we got any information about angular velocity. It takes 2.5 hours to make an orbit. So now I can convert that into radians per hour, right? Okay, so 1 orbit is 2.5 hours. I want my time units on the bottom, remember? the angle divided by time. So time units are on the bottom. So we're going to put 2.5, oops, 1 orbit divided by 2.5 hours. 1 orbit per 2.5 hours. Now I need to convert that to radians. So 1 orbit is 2 pi radians. That cancels the orbits, and I get 2 pi divided by 2.5. I'm going to write 2.5 as 5 halves. So I've got 2 pi divided by 5 halves. So I flip and multiply and get 4 pi over 5 radians per hour as omega. Then the linear speed in kilometers per hour is r times omega. Now that's r of the satellite, not r of the Earth. So here's the picture. We've got the Earth with a radius of 6,400 kilometers. Then a bit out here is the satellite. It's 1,800 kilometers more orbiting around the Earth. So the radius of the satellite is the sum of those two lengths. R is going to be 6,400 plus 1,800. 8,200 kilometers. So our linear velocity is r times omega. So 8,200 kilometers times 4 pi over 5. This will now be in kilometers per hour. And did I get that as a decimal? That's about 20,609 kilometers per hour. Next, we're asked to find out how far this satellite goes in 4 hours. Distance is rate times time. Take our, doing that right there per hour, multiply by 4 hours, and we've got the distance. So for part B, that distance is that rate, our velocity times time. So I'm going to take 20609, multiply it by our 4 hours, and that's about equal to 8243. Oh, I don't know where I got the 5 because 4 times 9 is 36. So let's go there. Kilometers. Okay. Too fast, too slow, just right? No answer? Okay, so a couple of problems on WebWork talk about how the clock hands move. So let me do one of those. Find the linear speed for the tip of the minute hand of the clock if the clock is 7 centimeters long. So my plan is, as before, to find my linear speed v, I'm going to multiply omega, the angular speed, times r. R is going to be 7 centimeters. So to figure out the angular speed of the minute hand, we figure out how many, what is its angular speed? I don't know. Tell me how to do it. How does it take the minute hand to get around the clock? 60 minutes to get all the way around the clock, right? So 1 revolution of the minute hand is 60 minutes, right? 1 revolution is 60 minutes. 1 revolution per 60 minutes is how long it takes that minute hand to get all the way around the clock. But a revolution is 2 pi radians. So 1 revolution is 2 pi radians. And so omega is going to be now 2 pi divided by 60 radians per minute, which is pi over 30. So the linear speed is the radius times the angular velocity. Our radius was 7 centimeters. Our angular velocity is pi over 30. And so now this is going to be in centimeters per minute. 7 pi over 30 centimeters per minute. I didn't write that as a decimal. Yes.
With that, so like it doesn't ask necessarily for like the units it wants it in, you just put it like in the most basic one?
Yeah, but if they're talking about centimeters, then
Do it
and
in
minutes, yeah, I'll tell you if you want to.
Okay, it's like to work the same thing. So
Yes.
it's just like, sorry.
Okay, so I think I've knocked that section out, maybe. Maybe so, maybe. That was still section 3.4. So maybe if you've got some time, do the chapter review problems. Let's jump on now to chapter 4. Chapter 4, we're going to graph our 6 trig functions. We're going to spend a lot of time graphing sine and cosine in section 4.1. Section 4.1 is graphs of the sine and cosine function. And so in that last section, or a few sections ago, we defined these trig functions in terms of the length of the arc around the circle, the number s. So we defined the 6 trig functions as functions of s, which is the arc length on the unit circle. So we're going to take that arc length here, there's s, and it can go round and round and round and round and round several times. So s can take on any number. It could take on a number like 4,000 pi. 4,000 pi, if you multiply 4,000 by 3, is about 12,000-ish, right? So it's a length. It's a length around the circle. I'm going to take that, and we can even generate negative numbers by rotating backwards. So s can be any number in the world. I'm going to take that length and I'm going to cut it and lay it out flat and call that the s-axis. And I'm going to define my trig functions as functions of the s-axis. So this axis right here is going to be f of s. S can be any real number, but I'm going to mark off the S axis in units of the reference angles that we have on the unit circle. 0, pi sixths, pi fourths, pi thirds, pi halves, blah, blah, blah. Okay. So I'm going to look at pi to be about that long, 2 pi, then we'll be able to have a minus pi, minus 2 pi, and so on. So these will go on forever and ever. And then the fractions of pi, this would be about pi over 2. This would be 3 pi over 2. This one out here would be 5 pi over 2, and so on. So down here would be negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. So those numbers correspond to the lengths of the arcs on the unit circle. The up and down values are going to correspond to whichever trig function we're graphing. So I'm going to graph the sine function first. I'm going to make that grid larger, and I'm going to remind you about our sine function. So let's consider f of s to be the sine of the number s. S, I said, could be any length. It doesn't have to have the little pi tacked onto it, but it's got to be some sort of radian measure. So there's a such thing as a sine of 2. 2 radians is a little bit bigger than pi halves. But for any real number, the sine of s describes the y coordinate around the unit circle. And in the unit circle, the y coordinates are always bounded between +1 and -1. So recall that the sine of s is always between +1 and -1, and s can be any real number. So let me make my s-axis down here. Get it kind of straight. All right, there's my s-axis. And put the f of s-axis here. And I'm not going to use the same scale. I'm going to say that this is 1 unit here. Now pi is about 3 of those, but I don't have room to put that on here. So let me make my s-axis a little bit tighter. Let's say that this is about pi, even though it should be 3 times larger than that. And then this would be 2 pi, and out here would be 3 pi. And if I had room, I'd put a 4 pi, but I don't. So let's go back to negative pi, negative 2 pi, negative 3 pi. I want to know the sine of those numbers. What is the sine of 0? Sine of 0 is 0. What is the sine of pi? And what is the sine of 2 pi? And then 3 pi. Sine of any multiple of pi is 0. Those marks that I just made there will represent the intercepts of the sine graph. It's going to cross this horizontal axis at all of those points. What number do I take the sine of to get 1? The sine of what number is equal to +1? Think on your unit circle. Pi halves. What's the sine of 3 pi halves? Sine of 3 pi halves is indeed -1. So anytime I'm back at the pi halves, which would be at 5 pi halves, right? So there's 1 pi half here, 3 pi halves here, 5 pi halves, 7, 9, 11, right? Every time I add another pi to those, I move up and down the y-axis on my unit circle. So if every other pi halves, this sine function takes on a value of 1. So here, at 3 pi halves, it's at -1. Then once I'm back up at 5 pi halves, we're back to 1. 7 pi halves, we're back down to -1. And it continues if I rotate backwards. If I start on my unit circle and I rotate to negative pi halves, I'm down at -1. So at negative pi halves, the sign is -1. At -3 pi halves, rotate around, I'm back at +1. Oops, I want a slash there. Slash, not a dot. Back up at +1. Then 2 pi is 0. This pi halves will bring me back down to -1. In between those numbers, for instance, at pi fourths would be half of a pi halves. We're at square root of 2 over 2, which is about, let's see, square root of 2 is about 1.4. Divide that by 2, that's about 0.7. So it's a little bit higher than a half. At pi over 6, which is 1/3 of the length of this interval, sine of pi over 6 is a half. So I don't want to plot those points. It's just going to give me points in between. So for the points in between here, pi 6th and pi 4ths, I'm going to get the 1/2 and the 0.7. And then it's going to duplicate itself because the angles between pi halves and pi, where are we in the unit circle between pi halves and pi? Which quadrant? Here's pi halves to pi. We're in quadrant 2. The sine takes on the exact same values in quadrant 2 that it does in quadrant 1. So when I'm over here at 5 pi over 6, I'm back to a half. This one up here, that's the pi thirds, is a half. 5 pi over 6 is back to this one. So I'm getting symmetry in here. Then in quadrant 3, it takes on those same values, but they're going to be negative. So between pi halves and 3 pi halves, I'm talking. 3 pi halves and 2 pi describe those angles and arc lengths in quadrant 4. So they're still negative. They're all going to do this. Now I've gone from 0 to 2 pi. So between 2 pi and 4 pi, I'm repeating the exact same values again. So we pick up that graph and hook it on end to end, and it does it again until I hit up here at 4 pi. If I wrap this thing in the opposite direction, then I'm starting off in quadrant 4, going to quadrant 3, quadrant 2, quadrant 1. So negative, negative, positive, positive. That keeps these values looking like that. They're negative because they're under the s-axis, still negative, positive, positive. Now we keep going back. But it's a cyclical function. It's a circular function that repeats its shape every 2 pi interval. It's periodic with period of 2 pi. In other words, in an interval of length 2 pi, 10, it does this shape over and over and over. If you just hook that little red piece onto itself, every interval of length 2 pi, then this graph goes on forever and ever in the s direction. All right, when we're graphing things though, we typically don't talk about the S f of x plane. We typically talk about the x, y plane. Well, the number S down there is just a dummy variable. If I want to call it X, I can. It doesn't mean the X coordinate on the unit circle, but it just represents a real number. So typically you'll see this graph labeled as the X axis and the Y axis, or the f of X axis. So this notation with the f of S is S, sine of S is just dummy variables. I can change this to an X and this to an f of X, and it's the same pairing between the real numbers X and the outputs f of X between -1 and 1.
Is it f of x because it's talking about a function?
A function of the variable X. If I used a T, I would have the sine of T plotted against f of T. Cosine is going to look very similar. Sine and cosine are cofunctions. What the heck does that mean? Cofunctions. If I know the sine of 30 degrees, then I have the cosine of how many degrees? 60. They take on the exact same values, but 90 degrees away. If I pick this graph up and shift it 90 degrees and lay it back down, I've got the graph of the cosine function. They take on the exact same values, but shifted by 90 degrees. I'm plotting in radians. 90 degrees is pi over 2 radians. So pick up these points that are crossing at multiples of pi, cross them at multiples of pi over 2, and that's what the cosine curve will look like. So let me flip my page and label my axis in that way for the graph of the cosine function. I'm going to stick with the f of S notation, but we'll change it. So now we're going to consider f of S is the cosine of S. So recall that the sine of S is the same as the cosine of 90 minus S. So it's the same graph. If I'm in radians, I better use pi halves. It's the same graph, but shifted over pi halves units. So if I put my S axis here again, and then my f of S axis, again, cosine on the unit circle is governed by the x coordinates of the ordered pairs on the unit circle. And there is no x coordinate larger than 1 or smaller than -1. So that means the cosine has that same range, that the cosine of any number S is bounded by 1 and -1. So I'm going to mark this again at 1 and at -1. And if these little babies here are of length pi, go back a little bit. We said I'm going to pick up all of the points from the sine function that crossed at multiples of pi, and I'm going to move them to the multiples of pi over 2. So the cosine graph is going to cross at every odd multiple of pi over 2. What I'm saying is that the cosine of pi over 2 and the cosine of 3 pi over 2 are all 0. Any odd multiple of pi over 2. So those on the graph show up as the intercepts. Cosine of what number is going to be 1? Cosine represents the x-axis on the unit circle. Cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of 4 pi is 1. Every even multiple of pi, cosine of that even multiple of pi is 1. Every odd multiple of pi, cosine will be -1. So cosine of 0, cosine of 2 pi, cosine of 4 pi, all of the even multiples of pi, cosine hits 1. Odd multiples of pi, cosine is going to be -1. So cosine of 0 will be 1. Cosine of pi will be -1. Cosine of 2 pi brings us back to 1. 3 pi brings us back to -1. And so if I graph it through here, kind of make it a little bit concave down between 1 and pi halves, and then a little bit concave up. What I've drawn there between 0 and 2 pi is considered one period of the cosine curve. If you hook that one on end to end to end, then you'll have the graph of the cosine function over and over. So it's going to come through here, down to 3 pi, cross at 7 pi over 2. Here's here's 4 pi. It's going to do the same thing back here. Down here, it hits -1 at negative pi. And then at 2 pi, it's back to 1. 3 pi, it's back to -1. So let me highlight one period of the cosine curve. This period again has a length of 2 pi. Then they start repeating their values over and over. So that is one period. The rest of the graph looks like that one period over and over and over. Please remember, sine, up, down, up. Cosine kind of looks like a big old bucket. The cosine function is considered an even function. An example of an even function is y is equal to x squared. It's symmetric to the y-axis. If this is considered my y-axis, this piece looks the same as that piece if I were to fold the paper along the y-axis. Cosine is even. The sine function is an example of an odd function. Function is odd if it's symmetric through the origin. So there is no reason to use S as the horizontal axis. We will use X, the vertical axis, housing the values of f of x will be called the y-axis. So the function f of x is equal to the sine of x, and the function, let's call it g of x, is equal to the cosine of x, where this is the input variable now, and that's any real number. It's not a degree number, it's a radian number. box over anymore. The sine function is an odd function. And the cosine function is an even function. In general, a function is odd if it has the same y value at the x and the opposite of x, but that y value is opposite in sign. It says that f of the opposite of x when compared to f of x are the same number, but opposite in sign. It flips about the x-axis. So for instance, the sine of pi over 4 is a positive square root of 2 over 2. But the sine of negative pi over 4, since on the unit circle that's in quadrant 4, is a negative square root of 2 over 2. Same value, but opposite in sign. A function's even if it has the same value and the same sign, just by changing the sign of the input. So this one says that g of the opposite of x is the same as g of x. That's in general as our definition of even and odd. When I write that in terms of the sine of minus x is minus the sine of x. The cosine of minus x is the same as the cosine of x. That's what I mean by even and odd. But it also compares the values of the sine and cosine in opposite quadrants on the unit circle. If you envision the unit circle here, the sine has the same values up, but opposite values down. The cosine has the same value here as it does in quadrant 4, has the same value in quadrant 2 as it has in quadrant 3. That's what that says.
So it's odd, it's symmetry of the origin.
Symmetric to the origin means an odd function. Think an example of a polynomial that's an odd function is y is equal to x cubed. Do you know what the graph of y is equal to x cubed looks like? Y is equal to x cubed passes through the origin, concave up here, concave down there. Same shape, but flipped about the origin. An example of the even function was y is equal to x squared. Whatever shape is on one side of the y-axis is the same on the other side. Do you know how the graph, say, of y is equal to x squared compares to the graph of y is equal to 2 times x squared? What does it look like? What if I take y is equal to x squared and plot it against y is 2 times x squared? It doesn't shift upwards. It gets tighter, right? It's a little bit tighter. So y is equal to x squared goes to the ordered pair 1, 1. But y is equal to 2x squared goes to the ordered pair 1, 2. It became a bit tighter. So it makes it taller. When we talk about our trig functions, they're bounded between 1 and minus 1. But if I take a number and multiply it, it stretches it away from the x-axis. If I multiply it by a fraction, it takes those numbers between 1 and minus 1 and squishes them closer to the horizontal axis. So putting a number in front of the trig function changes what's called its amplitude. The amplitude is half the distance between the tallest point and the lowest point. On our trig graphs, the tallest point is 1, the lowest point is -1. That distance is 2. The amplitude is half of that length, so the amplitude of 1. So each of these trig functions has an amplitude of 1. But if I were to compare the graph of f of x is some number times the sine of x, and g of x is some number times the cosine of x, I better use capital A. That capital A is going to be our amplitude. Ah, my pencil just came apart. Malfunction. A is called son of a biscuit. Guess we're going to red. Wait, here's a pencil. Please work. A is called the amplitude. But we got to worry about the sign as well. What if we look at the graph of y is equal to x squared and compare it to the graph of y is equal to negative x squared? It's reflected, right? Same thing can kind of happen here. If a is a negative number, it tips the graph upside down. So amplitude is a size. We're going to put it in absolute value. So I'm going to graph for you three different versions. F1 of x, I'm going to graph 2 times the sine of x. And F2 of x, I'm going to graph 1/2 times the sine of x. And I'm going to graph them on the same grid. So the first thing I'm going to do is I'm going to draw with a dotted line the graph of the sine of x. So here I need the pi's. I'll just draw it one period on each side, minus pi, minus 2 pi. And let's say that this height is 1 and that height is 2. Okay, so the sine of x did this, crossed at all multiples of pi, bounced between 1 and minus 1. Crosses at the multiples of pi, hits the 1 and minus 1, smack dab in the middle. So the dotted graph is f of x is the sine of x. This one went a little bit too tall over there. Get back down. It needs to be at 1. Now in this graph, if x is 0, pi, 2 pi, sine of those numbers were 0. So if I multiplied 2 by 0, I still get 0. So it's not moving any of those intercepts. Now the sine of pi over 2 is 1. So if x is pi over 2, this graph now has the ordered pair pi over 2, 2. Here's pi over 2 right here. This graph took that point and put it up to here. The zeros stayed the same. The sine of 3 pi over 2 was negative 1. If I put a 3 pi over 2 here, I would take my negative 1 and multiply it by 2 and get us a negative 2. So with a solid line, I'm going to draw the sine of 2x. It's going to go up to here, still cross at pi, hit down there at 3 pi over 2, and back to 2 pi. So there's one period. It doubled the height. It's going to do the same deal over here. The sine of negative pi over 2 was -1. So if I put that into this function, it's going to go down to -2. Same intercept, but it's going to take this ordered pair and smush it up to 2. And then back to the intercept. So this one is drawn with the solid line. I'm going to draw the next one using my red pen. What do you think happens on the next one? It's half as tall. So instead of passing through pi over 2, 1, it passes through pi over 2, 1/2. It's going to keep the intercepts. This one now is going to go to 1/2, keep the intercept, and this goes to 1/2. So one period is going to be half as tall. Same deal back here. Go to 1/2, 0, 1/2, 0. And multiplier controls the height above and below that horizontal axis. Whatever that number is going to be the tallest point. And then again, if that number is negative, it reflects the graph about the horizontal axis. Come on, pencils. There we go. If A is negative, the graph is flipped. Then stretched A units. Or compressed if A is a fraction. So I'm going to graph for you f of x is equal to -3 times the sine of x. So the minus sign says flip it, and the 3 says make the tallest and lowest points at 3 and -3. So it's flipped with an amplitude of 3. So when I'm drawing my sine curve and I start at the origin, 0, 0, then I'm going to go up to pi halves 3, down to pi 0, down to the 3 pi halves -3, back to 0 at 2 pi. I'll do it right there. Here's my horizontal axis. I got my words in the way, but I'm going to make each of these 1. So there's 3, and there's -3. The intercepts for the sine curve occur at multiples of pi. 0 to 2 pi will be 1 period. And then it's going to repeat that performance symmetric to the origin back here. Sine of 0, sine of pi, sine of 2 pi, minus pi, -2 pi are all 0. At the pi halves is where it hits its peaks and its valleys, odd multiples of pi halves. Typically, the sine of pi halves is 1. But in this case, I take that 1 and multiply it by -3. So the ordered pair at pi halves is pi halves -3. The sine of 3 pi halves is -1. So if I take the -1 and multiply it with the -3, I'm going to get a +3. So this upside down sine curve goes down, then up, and then back down for one period. Pick that piece up and glue it on to the back end, and that's what the period looks like over here. Up, then down. So it's going to here, here, and there, over and over and over and over. Okay, flip it, stretch it. Next thing I want to look at is what happens to our trig function if we squish something, a multiplier, into the x. Did you get this picture done? One, two, three, 4. So next, consider functions f of x is equal to the sine of some number times x. G of x is equal to the cosine of some number times x. I want to know what multiplying by a number to the x does to the graph. Doesn't pick it up and move it left and right, but it's going to affect horizontally. It's going to change things on the x-axis.
And negative is right, positive is left.
That's if you add or subtract. That's going to be called a phase shift. This number b is going to affect the period. The period was 2 pi. It took 2 pi little notches for the sine curve to do this and the cosine curve to do that. The number b there is either going to make that period happen over a wider interval or make it happen over a shorter interval. Typically, a period for these two functions begins when x is 0 and ends when x is 2 pi. This number will change the period. So typically, I know that the sine of 0 is 0. The sine of pi is 0. And the sine of 2 pi is 0. So if I represent what's in the parentheses with the number of b times x, if that's b times x, then b times x is 0, b times x is pi, b times x is 2 pi. Divide by b says that x is going to be 0, x is pi over b, x is 2 pi over b. It moves those intercepts to a new location, to 0, to pi over b, to 2 pi over b, and so on. It moves them, but it keeps the shape. It just takes what happens between 0 and pi and moves it to between 0 and pi over b. For instance, let's look at f of x is equal to the sine of 2 times x. So the first x-intercept occurs when 2x is 0. That's going to be when x is 0. The second x-intercept, so this is our first intercept. This is our second intercept. And this is our third. The intercepts on the sine curve. Let me flop the picture here. In one period, there are 3 intercepts on the sine curve. The first one, the second one, the third one. I want to find where these points have now been moved by putting a 2 in there. So the first one stays at the origin. The second intercept is when 2x is equal to pi. So that one's going to be shifted to pi over 2. The last x-intercept in one period was at 2 pi. That's going to be shifted to x's pi. The points in between follow. The ones used to occur at pi halves, they're now going to occur at pi fourths. So what the sine curve without that number next to the x did in an interval between 0 and 2 pi is now going to happen in an interval between 0 and pi. Let's. Yep, you're exactly right. So if this is 1 and that one's -1, and if that's pi and that's 2 pi, then I got to put my pi halves smack down in the middle. This one has intercepts at 0, pi halves, and pi. And the rest of the points follow. The rest of the points are going to be these right here. Come back. It's going to go between the zeros, up, and then hit the 0. Between the next 2 zeros, down, and then hit the 0 with symmetry. So between these 2 zeros, it's going to hit 1 right here at pi fourths. It's going to hit -1 at 3 pi fourths. So that's now 1 period. One period changed to 0 to pi. Then it's going to do it again between pi and 2 pi. So pick that up and move it again. At 3 pi over 2 is going to be another 0. And at 2 pi, and then smack dab in between, it's going to hit the 1s and the -1s. Back here, it's going to do it back to pi. There's pi halves. Those are going to be 0s. And it's going to hit a -1 smack dab in between and here. So 1 period occurs in the interval from 0 to 2 pi. In general, the length 2 pi divided by b will be called the length of a period for these shifted functions. So for f of x is the sine of bx, and g of x is the cosine of bx. The length of the period is now 2 pi divided by b. So if b itself is a fraction, 2 pi divided by a fraction is 2 pi multiplied by the reciprocal of that fraction. So the period gets longer. You'd love to see a longer period in both this class and in a trig function, but that's all I got for you today. You'll be done. Get caught up over the weekend in my class. Blow off your other classes for a little bit. And we'll be doing these graphs a bunch next week. That's all I got for you guys, and then we'll click on the off.